The input is at the gate of the MOSFET device, the output is measured at the drain of the device, and there is also obviously a bias here at the gate and at the drain, and the difference with a typical common source stage is that there is a resistor tied between the source and the ground. In order to ensure saturation, I'm going to perform a KVL inside this loop. I'm going to say that the input voltage is tiny in respect to the biases here, perhaps a few millivolts, 100 millivolts. So it won't really change my equation here on the KVL. I'm going to say that V0, right? We enter the negative terminal, V0, is equal to VGS. We enter the positive terminal here because it's VGS, VG minus VS, plus the current ID times RS here, the voltage drop from here to here. All right, this is the current flowing from the drain to the source, all the way from VDD to the ground. And from theory, I know that this current must be equal to this 1 over 2 mu n Cox W over L times VGS minus VTH squared. All right, for the saturation region. Now, if I try and solve this, all right, I get this huge quadratic equation. We can solve it, all right. We can solve it very easily by knowing the different values that are given to us by our exercises. Now, the voltage drop at the output must be equal to VDD minus the voltage drop here, IDRD. This would be the same as doing an KVL here, right? Similar to this. Now, in order to be in saturation, VDS must be more or equal to VGS minus VTH. How much is VDS? Well, VDS is V out minus the voltage drop here. Why? The same is as if I did a KVL here, or if I look at it logically and say that V out is composed of this voltage plus this voltage, all right? So it's V out minus IDRS. And how much is VGS? I found it previously here. V0 minus RS ID. I put minus VTH again here. And this gets simplified. And how much is V out? I found it here previously. VDD minus IDRD. More or equal to V0 minus VTH. I see that this must be true at the end if we have to be in saturation. So if I do all these calculations here, I get a current here, some voltages, etc. And I go here and I plug all these numbers, and this is not true. My assumption that we are in the saturation region is false. If I see that this is true, I get something like 0.8 is more or equal to 0.5, then I am certain that we are at the saturation region. Also note that there is no dependence on RS when we go and measure, when we go to ensure that we are at the saturation here, all right? If we are asked to find the gain of this configuration, we're going to need to draw the small signal model. For the small signal model, we are going to set all DC sources to 0, the DC sources, which means that the batteries must be short-circuited and the current sources must be open circuits. Therefore, I draw the small signal model of the MOSFET here. I draw a resistor tied between the source and the ground. I name this V1 instead of VGS because I don't want to confuse myself. and I want to be familiar with these typical circuits from circuit theory. So I don't remember any GS, VGS, or things like that. I remember simple V1, V2, V0, all right. I'm going to connect the input signal from here to the gate. This is shorted, all right. This is variable, so it must go into the small signal model. And there is a resistor tied between the drain and the AC ground here. Why? Because VDD must be shorted. I'll write it like this instead. That'd be the same thing. The current here must be GMV1, right? This is the dependent current source. The current flowing from here all the way to the ground must be equal to V out over RD. Notice that the arrow points from here to here because the out is measured from here to here. We must be careful with these things. If I do a KCL on D, I will get that GMV1 plus V out RD, because both of them go out of this node. And if I solve in respect to V1, I can eliminate V1 by knowing its relation to V out and the other known quantities, GM and RD. If I zoom the KVL on this loop, I'll get that V in must be equal to V1 plus the voltage drop here. How much is the voltage drop? The current flowing from here to here, which is GMV1 times the GM transconductance of the device plus the V1 here. Now, it's important to note that we don't have any channel length modulation, all right? And then the out over V in must be equal, if we solve these equations and replace V1 here, R minus RG over 1 over GM plus RS. This RD could be any other resistances here too that connect to the drain of the device and VDD, or between the drain and the ground. And the RS could be anything connected between here and the ground, or anything between here and a battery and the ground. In general, we say that this is the resistance tied between the source and AC ground. And this is the resistance tied between the drain and AC grounds too. Now, what if I had the channel length modulation? Well, if lambda is not 0, then again we set all the DC source to 0, and we make sure to connect a resistance tied between the drain and the source of RO. I will write it up here, and I'm going to say there is a loop here L2, similar to what we did before, and the current here flowing from the source to the ground, it's not GMV1 as we had before, but it's a more general VRS over RS, the two sources flowing, the two currents flowing inside the source. I would say that there is also a loop here over 1, and there is also a current flowing between the drain and the source of VRO over RO. If I do a KVL on L1, I'll get that V out, all right, the voltage between here and here, is equal to VRO, all right, plus VRS. We must be careful with the polarities here. We enter the negative terminal, so it's plus V out, and we enter then again a positive terminal, plus VRO, and we enter again a positive terminal, plus VRS. All right. Now, if we did a KVL on L2, we would work similarly. we enter a negative terminal plus V in, and then we enter a positive terminal is equal to V1 plus, again, a positive terminal, VRS. The voltage drop from here all the way to here. If I do a KCL on this node, I would get that GMV1 plus VRO over RO must be equal to minus V out over RD. Again, because all of these currents go out of the drain. Or more correctly, out of the node indeed. All right, so let's not get confused here. Now, if I do the KCL again on the source here on these terminals, terminal S, I'll get that GMV1 plus VRO over RO must be equal to VRS over RS. If I try to eliminate here the V1, I'll get that VRS must be equal to minus RS over RD times V out. This is very useful for me because now I can go inside this equation that was derived in KVL on L2, and I can replace VRS and get a relationship between V1 and V out. Now that I know the relationship between VRS and V out and V1 and V out and V in, I can go and on the equation 3, let's say, all right, and replace V1 and VRS. And I get this very beautiful result about the gain of the configuration when we have channel length modulation. All right, obviously, this is RS, all right, capital RS. And you can confirm that this is the same case as if we didn't have channel length modulation with RO being infinite. All right, you can divide with RO over here, and you will notice that some of these terms become zero, and it's the same thing as if we didn't have channel length modulation. Now, what if I had to measure the resistance Rin inside this configuration? Well, to measure input and output resistances, we must set all independent sources to zero. Set everything to zero. This includes my input small signal that I have at the gate. I draw the small signal model here. Again, I have channel length modulation. And the voltage X that I apply to my configuration in order to measure the Rin is applied to the gate, because at the gate is where I put my input signal. If I am to measure Vx over Ix, obviously Ix must be zero because it cannot flow really anywhere here, at least for small frequencies. In high frequencies, things are a bit stranger because we actually have some kind of capacitance between the gate and the source. This derives from the Cox of the device, all right? So we say that in small frequencies, we ignore this. The input resistance is infinite, all right? So everything is good to hear. Also note that it doesn't matter that we have channel length modulation. This doesn't play any role in my result. Now, what if I wanted to measure R out here, the resistance at the output? I will consider a general case where I have channel length modulation. Again, set all independent sources to zero. I have my configuration, the small signal configuration here. I set every source here to 0, alright, everything from the gates to the grounds. And I put a resistor, I put a voltage source between the drain and the ground of Vx. These are D connects to AC ground, alright, everything is fine. I will write it up here, and I also put some currents here. This the Ix coming out of my voltage source. There is a current flowing from the drain to the ground, Vx over Rd. There is a current flowing from the drain to the source that splits into GmV1 and the current flowing from RO. I call this IRO, and both of them connect to the source and become one current IS. I notice that the voltage here at V1 is minus the voltage at RS, so it's minus Vs, so it's minus RSIS. Alright, I must be very careful with the polarities in this configuration. We must always be careful with the polarities, but in this specific example, this is more and more difficult to imagine if we don't have a good foundation from electronic circuits. Now I can say that, well, the voltage drop from here to here plus the voltage drop from here to here must be equal to the voltage here, Vx, because Vx is applied to this node, which transforms to this node, and the negative terminal is all the way to here, right? The same ground. Now I can solve in respect to VRO. I can also say that what is VRS? We explained it before. VRS is minus V1. Therefore, VRO is Vx plus V1. Now I can take Ohm's law for the resistance RO, and I can say that, well, RO must be equal to VRO over IRO. Alright, this is RO here. So IRO must be equal to, how much is VRO? We found previously, Vx plus V1 over RO. How much is the current here that flows outside of the source? I take the KCL here, and I'll say that the current is equal to GmV1 plus IRO. Now I know that V1 is equal to minus Rs times Is. I replace from here and here the current. I go to this current, I place it here, and I replace IRO with this IRO. Therefore, I get this result for the V1. I notice now that I have V1, V1, and Vx, and I solve in respect to V1, and now I can safely eliminate it. In these configurations, when we do the small signal model, it's important for us, it's imperative for us to eliminate this V1 or VGS, however you want to call it. Now that I have a way to do it, I go and do a KCL on node D. Everything that flows in must be equal to everything that flows out. So Ix is equal to Vx over Rd plus the total current that flows, alright, this and this that become connected and become one Is. So I'll call this in general Is. And if I replace V1 from here, and what did I do here? And if I replace the equation 5, which is this equation, alright, I go to here and I say that Is is equal to minus V1 over Rs. And how much is V1? It's this little value here. So I replace everything and I get this result for my Ix. And now, if I simply say that, if I simply divide by Vx here and then I inverse my result, I get that Vx over Ix is in reality Rho plus Rs plus Rs GM Rho in parallel to Rd. This Rd could be any type of resistance type between here and the battery here and everywhere or everywhere else that could be resulting to the AC ground. And this Rs could be again anything sited in the source and the ground, or in general the AC ground between any battery and the ground and things like that. Alright? In general, we say that the output resistance has been boosted by Rs, this resistance sited between the source and the ground. This would be important because we don't want a lot of output impedance here, just so we don't mess with this circuit if we have anything else right here. We don't want to load our circuits. That's it. That's the common source stage with degeneration. In the more general case where we have channel length modulation. Alright? I hope you learned something useful here today. Subscribe to the channel for more. Study well and take care.